Good afternoon. I am Dr. Neel Kamal, Associate Professor, Department of Electrical and Electronics Engineering, School of Engineering and Technology, IIMT University, Meerut. So this is my second part of three-phase induction motor. So let us continue. So as per previous presentation, this is about the general course outcome of three-phase machines. So prerequisite we can escape. So this is the just contained in this presentation. We have the general introduction about three-phase induction motor, its slip and effect of slip on rotor parameters, and finally induction motor as a transformer we will discuss here. So principle of operation of three-phase induction motor, as we have discussed in our previous presentation also. Basically three-phase induction motor have two different parts, two different types. One is the squirrel cage type and second is the slip ring induction motor. These are based upon the construction of rotor. Stator remains same, but based upon the shape of the rotor we are having the two type of induction motor. One is the squirrel cage type induction motor and second is the slip ring type induction motor. Slip ring type induction motor basically have a advantage feature, just like we can add on rotor resistance inside it by using the slip ring systems. Induction motor runs synchronous speed. With synchronous speed, is it possible? No. Whenever induction motor get the speed equal to synchronous speed, so it means the relative speed will be equal to 0, and whenever we have the relative speed equal to 0, then we can say there is no production of torque. Means again it will reduce in speed, and when speed will be reduced means there is again a relative motion produced inside it, so we can say again starting torque it will have, so it means it again getting the speed. So we can say it never attain synchronous speed, but it always run with the speed slightly lesser speed with to the synchronous speed. Just like suppose we are having the two-pole motor. Two-pole motor means its synchronous speed will be equal to 3000 rpm, but its rotor speed will be near about 2900, 2980, 2920 rpm, like that. Suppose that we are having the four-pole induction motor, so its synchronous speed will be equal to 1500 rpm, so its rotor actual speed will be near about 1400 plus system, like 1440 rpm, 1420 rpm, 1480 rpm, like this, but just slightly lesser that of the 1500 rpm. So depending upon the number of poles here in the three-phase induction motor, we are having the rotor speed, but rotor actual speed, or we can say the three-phase induction motor actual speed will be lesser than the speed of rotating magnetic field, or we can say synchronous speed. So we can say induction motor always run with the speed lower than the synchronous speed, and this speed difference, which difference is difference between the synchronous speed, or we can say the speed of rotating magnetic field to the actual speed of the rotor. Ns is the speed of rotating magnetic field, and Nm we can say the speed of motor or speed of rotor we can say. So this difference Ns minus N, this difference is known as the slip. It's always expressed with the percentage and as a ratio of this difference to the synchronous speed. So we can say S is equal to Ns minus Nm upon Ns. This is the formula, and it always represented by the percentage we can say. So we can multiply it by the 100 to get the percentage system. So this is the formula for slip. We can say S is equal to N synchronous minus Nm minus upon N synchronous. In this system, suppose that S is equal to 0, or we can say slip is equal to 0. When slip is 0 here means n synchronous minus nm is equal to 0, or we can say rotor speed will be equal to synchronous speed. So S is equal to 0 is the stage where actual speed of the induction motor is equal to the synchronous speed, but it's never possible, because at this speed, at this stage, when rotor speed equal to synchronous speed, no torque will be provided by the motor, and where there is no torque is provided means it never have such type of system here. And second case, suppose that S is equal to 1 here. If S is equal to 1 here, this is the case of starting. How S is equal to 1 is possible? Suppose that in this formula, if we are having the Nm is equal to 0, or we can say suppose the standstill condition, that is known as the standstill condition, where rotor speed is equal to 0, means this component will be vanished, and n synchronous upon n synchronous means equal to 1, cancel out. So we can say S is equal to 1. So this is the case of starting of the induction motor, where we can say S is equal to 1. S is equal to 1 means rotor speed is 0 at this position. Now we will discuss about the different rotor parameter. We are having the different rotor parameter, means what the frequency of rotating magnetic field of rotor, what is the current of rotor circuit, what is the power factor, what is the impedance, what about the reactance. So these are the different components, rotor parameters we can say, on which slip always affect. So this topic is the effect of slip on rotor frequency, starting from here. So by this derivation we can conclude rotor frequency is equal to S multiplied by the F, where S is the slip of three-phase induction motor and F is equal to the supply frequency. In our India we are using supply frequency 50 Hertz, and slip of the three-phase induction motor have its range near about 1% to 4%, means in decimal system we can say S is equal to 0.1 to S is equal to 0.04, and having the frequency 50 Hertz. So by this system we can say rotor what will be the rotor frequency? Rotor frequency will be S multiplied by 50, or we can say frequency. So what will be the range of rotor frequency? Rotor frequency will have the range 0.5 Hertz to 2 Hertz, because suppose the S is equal to 0.5, S is equal to 1, just a minute. Suppose that 1% means S is equal to 0.01, and F is equal to 50 means if we multiply here S is equal to 0.01 to 50, so it will give us frequency, rotor frequency, that is 0.5 Hertz. And suppose that for 4% slip S is equal to 0.4 and frequency is 50 Hertz, means rotor frequency will be 2 Hertz. So rotor frequency, what is the meaning of rotor frequency? Rotor frequency means frequency of rotating magnetic field inside the rotor part. So it have range near about 0.5 Hertz to 2 Hertz. Second, effect of slip on rotor induced EMF. We are having two different conditions. One is known as the standstill condition, where rotor is at standstill, or we can say there is no rotation. And second is the running condition, where three-phase induction motor is running, or we can say rotor is on its running condition. So as per our earlier discussion about the slip system, we are having E2. E2 means rotor induced EMF per phase on standstill condition, and E2R. E2R means rotor induced EMF per phase on running condition. We are having the parameters, one stand for stator part and two stand for rotor part. So E2 means rotor induced EMF per phase for standstill condition, and when rotor is running we are saving it E2R. So this ratio E2R upon E2, this is the NS minus N upon NS. Why it is so? Because E2R is proportional to N and E2 is proportional to NS. induced EMF at standstill is proportional to its synchronous speed, but actual speed, this is the actual speed of rotor, and we can say, so when rotor is running E2R, so E2R is proportional to N, we can say. And if we are taking the ratio E2R upon E2, we can say Ns minus N upon Ns, and Ns minus N upon Ns is known as the slip, we can say. So E2R upon E2 is equal to slip, and in this case we can say E2R is equal to S into E2. So what is this? This is the induced EMF for rotor side and is equal to S into E2, where E2 is the rotor induced EMF at standstill and S is the slip. So we have such type of derivation for running condition, and for this is the relation between, we can say, for running condition and with the standstill condition. E2 is the induced EMF of rotor at standstill condition, and E2R is the induced EMF at running condition. Next, effect of slip on rotor resistance and reactance. As far as the resistance is concerned, we know that resistance is independent of frequency. Frequency remains same as at standstill condition and at running condition, but at running condition its reactance will be changed, because reactance have formula x2 is equal to 2 pi f L2 for standstill condition, and for running condition we are using here the nomenclature R. So x2R is the rotor reactance at running condition, so we are using here the frequency now Fr instead of F. So the formula will be x2R is equal to 2 pi Fr L2, and in previous slide we have already discussed that Fr is equal to S into F. So we can replace this Fr is equal to S into F, we can say. So finally we can conclude x2R is equal to X into x2. So we have the conclusion here that the rotor reactance at running condition is equal to the multiplication of rotor reactance at standstill condition with the multiply of slip here. Now what is the effect of slip on rotor impedance? What is impedance? Impedance is the resultant of these two parameters, resistance and reactance part. So we already have the formula Z2 is equal to R2 square plus X2 square, and it's under root. So at standstill condition, again I am saying Z2 is equal to R2 square plus X2 square under root. And for running condition, rotor current per phase on running condition, we can say Z2R we are using here R2 square plus SX2 square under root. So this is about the impedance system, and these are the triangles we are using here. At standstill condition, horizontal component is the resistance here and vertical components here is the reactance, and resultant of both will be the impedance here. So R2, X2 and Z2, these are the standstill condition parameters, and R2, X2R and Z2R are the parameters on running condition. Yeah. So this is the effect of slip on rotor power factor. Power factor means the ratio of the resistance to the impedance simply. For the rotor condition, we can say we are using the 2 subscription here, so we can say cos phi 2 is equal to R2 upon Z2. It is for the standstill condition where rotor is at standstill condition or rotor is not rotating at all. But on running condition we are using the R nomenclature here again, so cos phi 2R is equal to R2 upon Z2R, and Z2R, the value of Z2R is equal to, as per the previous slide, R2 square plus SX2 square. This is the current, effect of slip on rotor current. So I2 is equal to E2 upon, this is the impedance but at standstill condition, rotor current per phase on standstill condition. So I2 is equal to E2 upon under root R2 square plus X2 square. And on running condition, again and again I am repeating, we are using here the terminology. R means at running condition, 2 means rotor system, and R for running system. So I to R means rotor side current at running condition. So we can say E to R upon Z to R. And what is the value of E to R here? In as per our previous slide, we can say S into E2. And what about the Z to R system? Z to R is R2 square plus SX2 square. So this is about the rotor current at running condition. So these are the two equations. One is used for the rotor current for standstill condition, and second is the rotor current for at running condition. Now, induction motor as a transformer. We are having very much similarity of three-phase induction motor with respect to the transformer, because we all know transformer has two different part, two different coils we are using here in this construction of transformer. One is known as the primary side and second is known as the secondary side. Where we are putting the supply system, this is known as the primary side, and where we are using the load, we can say it as a secondary side. Transformer have its supply system in primary only, and in secondary there will be the induced EMF. But in this case, in both side, the primary side as well as the secondary side, frequency remain the same. But in case of three-phase induction motor, as it also have the two windings, one is the stator winding and second is the rotor winding, we can say. So stator can treat as a stator primary side of the transformer, and rotor we can treat as a secondary side of the transformer. So this is very much similar characteristic in this system. So like the transformer system, as we have the turn ratio like secondary to primary turn ratio, we can say in the three-phase system induction motor, we can say rotor turn per phase upon stator turn per phase. This is also the turn ratio, very similar to the case of transformer. But the main difference is there. In transformer case, we can say we are having supply frequency in both directions similar. In primary side as well as in secondary side, we are having the supply frequency same. In our India, we are using 50 Hz supply, earlier I have discussed. But in case of three-phase induction motor, in rotor side, we earlier have discussed about this. Rotor have frequency that is with the multiplication of slip. So it will be reduced greatly. So we are already having the range for the slip 1 to 4%. If we are having a slip 1 to 4%, we can have the range of rotor frequency that is 0.5 Hz to 2 Hz only. So this is the major difference where we are using in the 50 Hz supply in primary and secondary side in transformer, and as well as in the stator side we are using 50 Hz supply. But on the rotor side we are using maximum 2 Hz supply, rotating magnetic. So this make the difference between, otherwise we can say almost transformer action and three-phase induction motor action characteristics remain same. So this is why we can say we can model three-phase induction motor as a transformer. It work both system, transformer and three-phase induction motor, both working on the electromagnetic induction system. But we know transformer is the purely static device and transformer is the rotating type motor. It have rotating part, rotor, because it will work as a motor. In case of three-phase induction motor rotor part, basically we have the rotor R2 plus R2 upon S minus R2. These two are the, just a minute, these two we have add on to make a particular shape, that is the R2 plus R2 minus R2 plus R2 1 minus S upon S. So this R2 upon S is now have this shape. By using this shape we can say R2 is the pure electrical part. R2 is the pure electrical part. So it is the electrical resistance, but R2 upon S, R2 bracket start 1 minus S upon S, this part is not pure electrical part, it is the representation of mechanical part. It is the fictitious resistance we can say, and it is only the part that will convert into the mechanical power. Power consumed here will be converted by this system only. We have the rotor resistance of having two different part. One is the part of electrical and second part is mechanical part of resistance. That mechanical part of resistance in which power consumed will be converted into the mechanical power, because we have the motor concept according to the Fleming's left hand rule that if we feed electrical input in the electromechanical conversion system, it will convert it the mechanical output, and what mechanical power it will converted is given by this particular resistance. This is the resistance where mechanical power will be developed here by using the electrical input. So thank you very much about this presentation. In the next slide we will discuss about the starting, braking and other characteristics of three-phase induction motor. Thank you very much.